Welcome to Measurable Sets. We started these chapters a few lessons ago, and before started this chapter, we have learned the inner and outer measures, the measure of bounded open set, the measure of bounded closed set, and today, now we can start our main topic, measurable sets. So what is measurable sets? Definition. A bounded set E is said to be measurable if its outer and inner measures are equal. Sometimes it is called measurable in the Lebesgue sense. Or measurable in L. Okay. The common value of these two measures is called the measure, sometimes Lebesgue measure, of the set E and is denoted by ME. Let's start writing a theorem. Theorem 1. A bounded open set is measurable and its measure according to the new definition coincides with its measure as introduced before. And theorem 2. A bounded closed set. Here we talked about bounded open set, and a bounded closed set is measurable and its measure according to the new definition coincides with its measure as introduced before. Our third theorem is that consider that a bounded set E, any bounded set E, is contained in interval delta. If one of the sets E and the complement of E with respect to delta is measurable, then the other is also measurable. So let's prove this theorem. Proof. Suppose that E is measurable. That is, what is measurable set? The outer measure is equal to the inner measure. Then the outer measure, the difference between the outer and inner measure is equal to 0, as is obvious. By the last theorem in our previous lesson, the corollary was that the outer measure of the complement of E with respect to delta minus the inner measure of the complement of E with respect to delta is equal to the outer measure of E minus the inner measure of E, and it's equal to 0. So we get that if this side is true, the right hand side is true, then left hand side also should be true. So the outer measure of the complement of E with respect to delta is equal to inner measure of the complement of E with respect to delta. And theorem 4. Suppose that a bounded set E is the union of a finite or countable numbers of measurable sets which are pairwise disjoint. It means that E is the union of EKs where EKs are disjoint and pairwise. This means that the intersection is a null set and they have no common elements. Okay, then the set is measurable and the measure of this set is equal to the sum of the measure of all EKs. And we get these two theorems. The union of finite or countable number of measurable sets is measurable set. Also, the intersection of finite or countable number of measurable sets is measurable set. So here we have the theorem 7. The difference of two measurable sets, the difference of any measurable sets is a measurable set. Let's prove. Let E be the difference of E2 and E1, where E2 and E1 are measurable sets. And let delta be interval which contains E1 and E2. Then E is equal to E2 intersection the complement of E1 with respect to delta. Here E2 and complement of E1 with respect to delta are measurable. So, by the previous theorem, E is measurable. We proved this theorem. And theorem 8. Let E1 and E2 be measurable sets, any measurable sets. If E1 is a subset of E2, then if E1 is a subset of E2, then the measure of E2 minus E1 is equal to the measure of E2 minus the measure of E1. So theorem 9, let sets E1, E2, E3 be measurable if each the sets are the subset of each other's. E1 is a subset of E2, is a subset of E3, and etc. And if E, the union of this E case, E is a bounded set, then the measure of this set E, of a given set, is the limit of the measures of all ENs when n approaches to infinity. And our final theorem, let the sets E1, E2, E3, and etc. be measurable as above. If these conditions are satisfied, it means that all the ENs are the subset of E1, and if E is equal to the intersection of E k's, where k is equal, k starts with 1 to infinity, then the measure of E is equal to the limit, when n approaches to infinity, the limit of the measures of En.